Viitorul e al tău, noi punem temelia. UDCP, construim pentru România. UDCP, Universitatea de Construcții București.
Good morning, everybody. Thanks all for coming here, and I'd like to take this opportunity to have a very deeply felt acknowledgement to the Japanese people who supported us for many, many years in different types of projects. And today we have a very special day when Japan is again with us. And we do hope that we will launch a new cooperation in different fields related to infrastructure and buildings as well. I would like to salute the presence of the Ambassador of Japan, Mr. KATAE, today with us. It is the first time he is visiting our university, but I told him that it is not for sure the last time, because we have to show him a lot of outcomes of the JICA project here in Romania, and it is very, very important for us to show that the seeds that Japan planted here many, many years ago have very strong and tasteful fruits. Also, I'd like to salute the presence of the Romanian government here today, with Mr. țOLE from Ministry of Development, Dr. Arafat from Ministry of Internal Affairs, and Professor Pisecaro from Ministry of Research, who joined us today. And we have a brilliant opportunity to have 3 professors from Japan, very famous. Professor KUSUNOKI, Professor Kisada, and Professor Akiyama. And I think that the straw that stir everything for today is Ambassador Dranga, and we have to take the credit for Ambassador Dranga. And one very, very important partner in having this event today is IHI from Japan. And I would like to extend my gratitude to IHI for supporting this event and for being today with us. So, with no further delay, I will move to the schedule. So we'll have some presentations in the beginning. There are some changes in the presentation in the beginning, but first of all, I would like to ask Mr. țOLE, Secretary of State in Ministry of Development, to have an address.
Vă mulțumesc mult de tot, domnule ambasador, domnule secretar de stat, domnilor profesori, domnule rector, stimați invitați. Suntem onorați să participăm în deschiderea seminarului tehnic care se adresează creșterii rezilienței construcțiilor inginerești la seism, temă de interes în relațiile de cooperare dintre România și Japonia, mai ales în contextul în care Ministerul Dezvoltării Lucrărilor Publice și Administrației are o tradiție îndelungată de colaborare cu importante instituții de profil în ceea ce privește problematica a reducerii riscului seismic, respectiv cu Asociația Japoneză de Izolare Seismică și Ministerul Terenurilor, Infrastructurii, Transportului și Turismului din Japonia.
Distinguished guests, it is an honor for us to take part in the opening of the technical seminar on improving the earthquake resistance of the engineering structures. This is a topic of interest in the Romanian-Japanese cooperation relationship, particularly considering that the Ministry of Development, Public Works and Administration has a long history of working with significant organizations in the field of seismic risk reduction, including Japan Society of Seismic Isolation and the Japanese Ministry of Land, Infrastructure, Transport and Tourism of Japan.
De asemenea, doresc să evidențiez și rezultatele cooperării româno-nipone în implementarea proiectului JICA, de cooperare tehnică pentru reducerea riscului seismic la clădiri și structuri, care a avut ca principale rezultate dezvoltarea și implementarea de soluții de consolidare seismică a clădirilor existente, îmbunătățirea codurilor de proiectare seismică, realizarea de investigații cu echipamente avansate, precum și organizarea de strategii de specializare profesională.
I would also like to draw attention of the outcomes of the Japan-Romanian collaboration in carrying out the JICA Technical Cooperation Project for seismic risk reduction of buildings and structures in Romania. Out of the results, I would like to underline the development of the training programs, the improvement of the seismic design codes, the implementation of seismic strengthening measures for already existing buildings, and the use of the state-of-the-art equipment for investigation.
Ministerul nostru consideră tematica reducerii riscului seismic drept una dintre cele mai importante teme pe care le gestionează. Ca minister responsabil cu dezvoltarea regională, amenajarea teritoriului, urbanismul, construcțiile și lucrările publice, avem un rol extrem de important în perioada de predezastru, cel de analiză și planificare a teritoriului, realizarea de hărți de risc, cel de reglementare tehnică a proiectării și execuției lucrărilor de construcții și mai ales cel de a dezvolta și de a implementa programe de investiții în consolidarea clădirilor publice și private cu vulnerabilitate seismică ridicată.
Reducing seismic risk is one of the most significant concerns that our ministry oversees. As a ministry responsible for regional development, special planning, urban planning, construction and public works, we play a crucial role in the pre-disaster phase, in the analysis and planning of the regions, in risk map generations, in the regulatory oversight of both design and execution of construction, and above all, in the design and implementation of the investment programs that reinforce public and private buildings with high seismic vulnerability.
Problematica riscului seismic trebuie abordată concomitent pe mai multe paliere, care presupune eforturi concertate ale tuturor categoriilor de factori implicați, reprezentați și la evenimentul de astăzi. Aș menționa aici importanța cercetării fundamentale și aplicate, rolul universităților, a mediului profesional și instituțiilor de cercetare, precum și necesitatea cunoașterii reale a situației din teritoriu pentru fundamentarea politicilor, importanța existenței unei viziuni strategice naționale și a unor instrumente de punere în aplicare a acesteia, reglementări tehnice de proiectare, instrumente de finanțare și de monitorizare.
Seismic risk is a problem that has to be addressed synergetic on multiple fronts with coordinated actions from all stakeholders, including those involved in today's event. Here, I would like to underline the significance of fundamental and applied research, the role of academia, professional associations and research centers, as well as the necessity of having a national strategic vision and the means to carry out together with the technical design rules, funding sources, monitoring tools, all of the above applied in the context of accurate knowledge of the actual state of affairs on which to base policies.
De asemenea, nu trebuie uita faptul că pe lângă problematica riscului seismic, ne confruntăm și cu alte provocări care trebuie abordate complementar, sustenabilitatea mediului construit, presupunând și abordarea aspectelor de eficientizare energetică, reducerea riscului la incendiu, creșterea rezilienței la schimbări climatice, inclusiv aspecte legate de riscul la inundații și altele.
Not to be overlooked is the fact that, in addition to the problem of seismic risk, we additionally face challenges that need to be dealt in tandem with one another in order to ensure the sustainability of the built environment. These issues include fire risk reduction, increased resilience to climate change, including flood risk issues, and others.
În acest context, Ministerul nostru a demarat în ultimii ani un pachet complex de reforme susținute de programe extrem de consistente de investiții pentru asigurarea unui fond construit de calitate și rezilient la riscurile naturale, astfel că o serie de acțiuni dedicate reducerii riscului seismic la construcțiile existente au beneficiat de o finanțare substanțială atât din fondurile europene prin PNRR, cât și din bugetul de stat. Dintre acestea, aș enumera câteva contribuții specifice privind problematica reducerii riscului seismic, care sprijină România în eforturile de reducere a riscului seismic, de îmbunătățire a calității vieții și a fondului construit.
In light of this, in recent years, in order to guarantee a high-quality built environment resilient to natural disasters, the Ministry has initiated a comprehensive package of reforms that are backed up by substantial funding. As a result, several initiatives aimed at lowering the seismic risk of existing buildings have received significant funding from the state budget as well from the European funds via the National Recovery and Resilience Plan. Out of all of them, I would like to highlight a few noteworthy contributions to the field of seismic risk reduction that help Romania in its endeavors to lower seismic risk and enhance the built environment and quality of life.
Elaborarea primei strategii naționale de reducere a riscului seismic al clădirilor, strategie complementară cu cea privind renovarea energetică a clădirilor.
Development of the first national strategy for seismic risk reduction of buildings that is complementary to the strategy on energy renovation of buildings.
Revizuirea legislației primare și secundare privind reducerea riscului seismic prin actualizarea legislației, a cadrului normativ privind proiectarea clădirilor la acțiuni seismice și realizarea de intervenții integrate, evaluarea vizuală rapidă a clădirilor.
Revision of primary and secondary legislation on seismic risk reduction by upgrading and updating the regulatory framework, improvement of the regulatory framework on building design for seismic actions, and integrated interventions, rapid visual inspection of buildings, and so on.
Diversificarea programelor de investiții și asigurarea finanțării și implementării eficiente a programelor de investiții în domeniu, finanțate din fonduri europene sau naționale, pentru a accelera rata de consolidare a clădirilor publice și private.
Diversify investment programs and ensure efficient financing and implementation of investment programs in the field financed by European or national funds in order to accelerate the rate of consolidation of public and private buildings.
Modificările aduse de noile programe vor genera o creștere semnificativă a ritmului de consolidare, însă situarea majorității teritoriului într-o zonă cu seismicitate ridicată, precum și vechimea fondului construit din punct de vedere al asigurării unei protecții antiseismice corespunzătoare, face ca această problemă să nu poată fi rezolvată exclusiv prin implicarea statului. În acest sens, este necesară realizarea de lucrări din mai multe surse de finanțare, iar succesul implementării acestora depinde de programele de investiții, depinde de eforturile făcute de fiecare dintre noi pentru a realiza investiții de calitate.
Even the majority of Romania is located in a high seismicity area, the built heritage is too old to provide enough earthquake protection, so state involvement alone will not be sufficient to tackle this problem. Nevertheless, the changes brought about by the new programs will significantly accelerate the pace of retrofitting. In this regard, it is essential to carry out projects from several funding sources, and every and each one of us should make the effort to carry out high-quality investments if we hope for their successful execution.
Astăzi, în cadrul acestui seminar, specialiștii din diferitele medii ale practicii profesionale vor dezbate aspecte legate de practica tehnică în proiectarea, execuția, consolidarea seismică, instrumentarea și monitorizarea seismică a clădirilor, dezbateri ce vor aduce contribuții importante în sprijinirea demersurilor naționale de realizarea unor proiecte de transfer tehnologic pentru implementarea de tehnologii inovative, de consolidare seismică a clădirilor existente, dar și de schimb de bune practici în ceea ce privește reducerea riscului seismic.
Today, during this seminar, experts from various fields of professional practice will engage in debates that will significantly support national efforts to carry out technology transfer projects for the implementation of cutting-edge technologies for the seismic strengthening of existing buildings, as well as to exchange best practices, best available techniques in the seismic risk reduction field. These debates will center on issues related to technical practice in the design, execution, seismic strengthening, instrumentation, and seismic monitoring of buildings.
Da, vă mulțumesc mult de tot și doresc succes lucrărilor, seminariilor, având în vedere importanța temei. Mulțumesc!
Now we'll move to, I mentioned that there is a slight modification in the program, so we'll switch to Mr. Seiichi ONODERA, Ministry of Land, Infrastructure and Transport of Japan, Deputy Minister for International Projects of Japan. You have the floor.
Thank you. Distinguished participant, everyone, good morning. I am ONODERA Seiichi, Deputy Minister for International Projects of Ministry of Land, Infrastructure, Transport and Tourism, MRIT, in Japan. On behalf of the MRIT, I would like to deliver my opening remarks. I would like to thank you for inviting us to this very meaningful workshop and for providing us with a valuable opportunity to participate in. I've heard that the workshop will focus on the theme of infrastructure maintenance, such as bridges and buildings. Until now, Japan has actively developed our infrastructure since the mid-1960s, but recently these infrastructures are gradually becoming aged. For example, in Japan, the percentage of road bridges that are more than 50 years old after construction is expected to increase sharply from 30% in 2020 to 75% in 2040. The problem of aging infrastructure leads to serious problems. The first problem, aging infrastructure, is safety and life-threatening issue. In Japan, 9 people were died in a sudden accident when the aging ceiling panel of a highway tunnel collapsed in 2012. MRIT considered this accident as very serious and decided to address the problem of aging infrastructure by promoting preventive maintenance. The second problem is the cost of maintenance. In Japan, planned maintenance in advance of serious damage can reduce life cycle cost and enable infrastructure to be used longer, rather than major repairs after damage becomes serious. The importance of such planned maintenance or actions of the MRIT will be introduced by our staff's lectures in today's seminar. In Japan, the industries, universities, governments, and private sectors are now mobilizing all of our technology and wisdom to strategic infrastructure maintenance. I think that these advanced technologies and knowledge in the field of maintenance that we have cultivated through such efforts can contribute to the problems of aging infrastructure in other countries as well. I hope that the action of the MRIT, as well as the researches conducted by Professors Hisada, Akiyama, and Kusunoki, and the technologies and the services provided by IHI, will contribute to ensuring the safety and efficient maintenance of infrastructure in Romania. Finally, I would like to end my remarks by expressing my hope that today's workshop will be meaningful and will contribute to the further development of cooperative relations between Japan and Romania, and as well as to the further development of the Romanian nation. Thank you for your attention. Thank you.
Thank you so much. And now it's my privilege to invite His Excellency, Mr. Takashi KATAE, Ambassador of Japan in Romania, to address the welcome speech.
Director State Secretary Arafat, State Secretary Zole, State Secretary Priseka, and Deputy Ambassador Florin, Deputy Minister Seiichi ONODERA, Professor KUSUNOKI, Isada, and Akiyama. Good ladies and gentlemen, distinguished guests, good morning. Bună dimineața. Today, I'm very pleased and honored to be able to attend this workshop on seismic rehabilitation and maintenance of buildings and bridges. Improvement of resistance to earthquakes and reduce the seismic risk is one of the most crucial areas in which Japan and Romania have been collaborating very closely and successfully throughout the years. Since the early 2000s, when Japan International Cooperation Agency, JICA, first started to run the technical cooperation on the topic in Romania. As you are well aware, Japan is a country where earthquakes hit often. You may remember the disaster that hit Japan on March 11, 2011, the Great East Japan earthquake, which has also one of the strongest earthquakes that my country ever experienced in its recorded history. During the 2011 earthquake affected Japan, the Romanian people and the government of Romania stood by Japan and kindly supported us in various forms. Even now, after all this time, I would like to sincerely thank you all for that wonderful support. As you may know, this year also, right on the New Year's Day, a magnitude 7.6 earthquake hit in the Noto Peninsula of Japan and of Ishikawa Prefecture, and very sadly, it also resulted in many human casualties in addition to material ones. People of Japan have to live with earthquakes and adapt technologies constantly to prevent or minimize their damage. I have learned that Romania also went through some terrible earthquakes, like the one of the March 4, 1977, which also resulted in a large number of casualties, especially in Bucharest. I also know that people here talk about the large earthquake that may hit Romania again in the near future. From these perspectives, Japan and Romania have the same difficulties and challenges on earthquakes. As Rector Vakarian mentioned, JICA conducted a project entitled the Technical Cooperation Project on the Reduction of Seismic Risk for Buildings and Structures in Romania, together with the concerned Romanian authorities, including the Technical University of Civil Engineering in Bucharest from 2002 to 2007. In this project, JICA sent 44 Japanese experts to Romania and welcomed 29 Romanian specialists and researchers to Japan. The Professor Vakarian at the time was directly involved in the project and was also the director of the National Center of Seismic Risk Reduction at the time. Thanks to his wonderful efforts, this project has led to useful applications in Romania and good cooperation with Japan on this project continuing into this very day, as well as we can all witness today. Professor Konstantin Budan from UTCB has also continued to make wonderful efforts to develop the working relationship with Japan in the field of seismic research, and he travels to Japan annually to teach there even to this today. I would like to express my sincere gratitude to Professor Vakarian and Budan, as well as their colleagues and the entire team from UTCB, who are not all named here, for their wonderful efforts and commitment to keep Japan as a main partner in seismic research and reduction in Romania. I'm also extremely glad to see the presence of such important guests from Japan here today. Japan obviously places great importance on the cooperation with its strategic partners, Romania, in this area. Since one of the topics of today's workshop covers bridges, I would like to announce to you all that the bridges over the Danube River in Vrancea, which was built with the cooperation of Japanese company IHI, already incorporates Japanese earthquake resistance technology. So here we have a concrete example of Japanese anti-seismic technology incorporated in an important Romanian infrastructure project. I am so proud and honored to see that the cooperation between Japan and Romania in this field has already reached this stage. I sincerely hope that this kind of good practice in cooperation between Japan and Romania will be repeated many times in future. In closing, please allow me to thank you all again for the invitation and to wish you all a successful and fruitful event today. Thank you very much. Vă mulțumesc pentru atenție.
Thank you so much, Your Excellency. As usual, Japanese side is very open and very eager to cooperation, and I do hope that at the end of the day we will see a joint, very strong will for future cooperation. We discussed, actually everybody mentioned disasters and measures before disaster and during. So I will take the opportunity that Dr. Arafat is here with us today because he is the key person dealing with the effects of the disasters, and we will make him a very happy guy if we will prepare from an engineering point of view such as not to be a disaster. Dr. Arafat, please.
Your Excellency, dear colleagues, I am very sure that we will be very happy if we know that there will be no disasters, because if the work is done on this side, then we should not be having disasters in the future. We will have just events. But the last period have shown us that it is not so worldwide. We see more and more challenges. We've seen the earthquakes in Syria and in Turkey last year and the devastating impact they could have. And we know that we are living in a city which is with a major seismic risk. And this is not all. You're talking about infrastructure and bridges. The Department for Emergency Situations ran a study on the situation of maintenance of viaducts and bridges in Romania a few years ago together with the Ministry of Transport. And our conclusions were not very optimistic, at least looking at the periodicity and how the maintenance is run. So here I encourage a lot that this is an issue we need to look at because it impacts our resilience and our critical infrastructure. So to cut it short, from our point of view, prevention is the best way ahead. And prevention is done through retrofitting of buildings, through projects like the ones that Secretary of State Sonia mentioned, and through working with experts and with countries that have a very high expertise in this. And here I'm happy to welcome our friends from Japan, because I know that this is a long-lasting relationship. I was in Japan. I was impressed on how you do everything, starting with preparing your population up to preparing your country and your citizens for disasters. So I hope that we will be able to join you in such experience and to see what we can do in Romania also to become more resilient from this point of view. So thank you again and good luck with your works today.
Thank you so much. Department of Emergency Situation and General Inspectorate for Emergency Situations are very reliable and long-standing partners of the University, of the Building Research Institute, of the National Institute for Aerospace, Institute for Geography of the Romanian Academy in developing projects, and we are very much look forward to continue this kind of cooperation. Thank you so much. So this concludes the first part of the seminar, and we are a little bit late, but we will compress the time, and we'll move to the technical presentations. And for the technical presentations, we will have two moderators, one moderator under the coffee break from Romania and the moderator from Japan after the coffee break. So I will invite Associate Professor Viral Popa to take the first 4 technical presentations.
So I will introduce now Professor Koichi KUSUNOKI from the University of Tokyo. Professor KUSUNOKI is a program director at the Cabinet Office of the Government of Japan, and he will present us the outline of the national project Seiichi to tackle this natural disaster. Please.
Thank you for coming here to tackle with natural disasters. We are facing the same problem. Even though the distance between Romania and Japan are so far, it takes about 20 hours to fly. But still we are facing the same problem until we solve all problems. It takes time. Then as ambassador and Radu-san pointed out, we have been having a very good and friendly cooperation on the tackling with natural disasters. I found some photos in my computer, and this was the photos conducted the previous JICA project about 20 years ago. Can you imagine this? That is Professor Radu. He has been very young. And myself, oh, I cannot believe that. 20 years ago. Then, of course, still we are suffering the earthquakes and disasters. And also now it's quite important how to maintain the infrastructures, not to stop the daily act of the human being around the infrastructures. So in Japan, the Cabinet Office decided to concentrate on some quite important issues to develop the new technology. So that's called SIP. SIP is the abbreviation of the cross-ministerial strategic innovation program led by the Cabinet Office. It's not only related to the disaster maintenance. There are many widely spread topics selected. There must be the multi-ministerial project. Then for the first time, it started in 2014. You can see the title of the project. For example, power electronics, structural materials, automated driving, and also social resilience, which was related to the disaster reduction and preparation. The second term started in 2018. Then another 12 programs were selected by the Cabinet Office. Then, for example, the security, IoE, AI hospital, and in them you can find another national resilience, which was related to the disaster mitigation. You may know that Japan has almost all kinds of natural disasters, including earthquake, volcanoes, typhoon, flood, tsunami, and so on. For example, this one is a map of Japan, which is indicating the predicted earthquakes. Unfortunately, so many earthquakes are predicted right now. Then the highest probability I'm sorry, this map is showing the history of the earthquakes. Unfortunately, we got a pretty strong earthquake in 2011, Pacific coast of the Hoku earthquake. The magnitude was incredibly 8.4. Unfortunately, so many people were killed. Then as the Japanese ambassador pointed out, unfortunately, we got a pretty strong earthquake in Noto Peninsula in 2024. This year, New Year Day, earthquake never care what day they come. Just New Year Day, the earthquake happened. Right there, the facing to the Japan Sea. Then the extent that was there, the magnitude was, as Ambassador said, 7.6. Then more than 200 people were killed due to earthquake. Fortunately, nobody was killed due to tsunami. Tsunami hit the area, but they evacuated. Then now we have a lot of sensors on the ground to measure the seismic intensity. Then the calculated seismic intensity hit the highest intensity according to the Japanese scale, which was a 7 in some cities. Then the geographic characteristic is quite unique in this prefecture. You can see very narrow peninsula. Then earthquake hit this area. We don't have enough number of roads. They were seriously damaged. Then we lost the way to get to the affected area. That was quite strongly related to the disaster management and also infrastructure management, how to maintain the roads to prevent this kind of catastrophic event. And many all the small towns were isolated because they lost the way to get out of the area. Now, for example, this one was a hospital, but unfortunately severely damaged. It looks like very old because this building is using the round bar, quite smooth round bar, which is not common right now. So that means this building was designed according to the previous building code. Then according to the Japanese law, the owner is recommended to evaluate the seismic capacity of their house building designed according to the previous building code and strengthen if needed. But unfortunately, this building was not retrofitted. That's why it collapsed. Then this photo is a quite shocking photo, but this building overturned totally. And sometimes, during some other earthquakes, some buildings overturned like this. This is not the first case. But what was the first case was, there was a 3-story timber house right here. You cannot see, but 3-story timber house was there. New Year Day in Japan, families got gathered to celebrate the New Year Day. Then unfortunately, that family was inside the building, inside the house, which was totally crushed. Then unfortunately, husband lost his wife and daughter here. So, still in Japan, some people were killed due to the collapse of the building. And some other buildings also inclined a lot, but fortunately didn't overturn. The school building as well. This building was retrofitted. So that's why the collapse was prevented. The New Year Day, so there was no student, fortunately. But thanks for the retrofitting, the building was okay. A little bit inclined, but it's okay. The building didn't kill the student, even if the students were inside. And houses collapsed a lot. So still we are facing the same problem. Once earthquake hit Japan, still some people were killed due to the collapse of the buildings. Like this. So what we have learned from the earthquake damage. are shown on this slide, always earthquakes is much smarter than us. Then the earthquake always teach us something new, with losing the lives of the people. Then just from last year, the third term of SIP got started. Again, the Cabinet Office selected this time 14 subjects. The one of them is the disaster mitigation. Development of a smart network for disaster mitigation is the current title. Then the budget size is huge, about $24 million per year for 5 years. Then now, today, we have Professors Kisana from Tohoku University and Professor Akiyama from Waseda University, the leading universities in Japan. They are working for the development of a smart infrastructure management system. These two subjects were selected by the Cabinet Office and started from last year for 5 years. We are, of course, collaborating. Like in Romania, you are collaborating between the Ministry of Construction and the Ministry of Transportation to promote the seismic evaluation and retrofitting, and also to promote the bridge management, the same. Then, as I said, this SIP project should be the multi-ministerial project. This is the structure of our central government. The cabinet is the top of the structure. Then we have many ministries. The ministries and the agencies in the letters are involved in our project. Like, of course, Ministry of Public Management, Ministry of Education, Ministry of Health, Ministry of the Economy, the Ministry of Land Infrastructure and Transport, and so on. Then the National Police Agency and the Self-Defense Agency are also involved. And what we are going to do is, what is the current difficulties? Here you can see the current difficulties in Japan against natural disaster. Earthquake happened, then we can see the TV program, which shows overturned building. Then we recognize, it's a serious situation. But it's quite difficult. Where the affected, collapsed building were in the affected area. We cannot specify the locations of the damaged building, damaged people, and damaged roads and so on. But it's quite important. That's the first step to countermeasure the disasters. Then, unfortunately, the frequency of the earthquake, typhoon, flood is increasing. Most probably because of the global warming, especially for the flood and the typhoon. Then it happened once per 5 years, 6 years before, but right now, almost every year or every other year, really strong typhoon hit Japan. Unfortunately, it should be in August or September, but unfortunately, right yesterday, the first typhoon was born, then heading to Japan right now. The typhoon will get to Japan the day when I will fly back to Japan. I'm pretty concerned about the situation of typhoon right now. Then, on the other hand, people get used to the information about the disasters. Like me, today, typhoon is coming. Or earthquake happened and sometimes tsunami warning is announced. Then some people go to the coast side to see the tsunami. It's quite dangerous. Then it's quite difficult for current central government to make the people evacuate. That's pretty big concern right now. So what we are going to do is we are going to develop a cyber digital twin world in a computer world to grasp the damage situation, then immediately we can conduct some numerical simulation to predict a little bit near future. Like what happened if the aftershock hit the same area? What happened if the typhoon moved to the next prefecture? That's our main objective of this project. So we are going to use the digital technology to tackle with the natural disaster. So this is somehow the idea, the schematic of our project. The disaster happened in the real world, of course. But immediately, the information, damage, everything will be detected by the satellite image, drone, the sensors in the building, in the rivers. Then we develop the digital twin in the cyber space. Then conduct a numerical simulation or required analysis. But if we just give the raw data of the analysis to the decision makers, they never care. That kind of raw data cannot support the decision makers. We need to translate the raw data from the analysis to the decision makers for supporting them. Then comes back to the real world to support and take the action against the disaster. Then the typhoon is moving second by second, and the earthquake, the aftershock will come. As such, the disaster can change time by time, second by second. So this kind of cycle goes around during the very serious disaster period. This is the structure of our project. I'm sorry, the letters are too small, but I hope you can have the handout of my presentation. We have 5 subtopics, subgroups from A to E. A is a detection team. They are going to use satellite, drone, IoT sensors installed in, let's say, the microwave, light, air conditioning system. You have sensors in your home everywhere. We're going to connect such IoT sensors to the system to detect the situation. That's subgroup A. Subgroup B is one of the very, very challenging group to change the people's mind to evacuate. That's not only the technical issue, but also somehow social issue. How to change the people's mind to make them evacuate. That's group B. Group C is also another quite challenging topic, to share the data among the agencies, such as self-defense agency. It's quite similar to military, but our government never called it military, so it's a self-defense agency. And police department, firefighter department, ambulance team, their immediate response team. Then historically, it's not easy to share the information among such very important agencies. They tended to hide the information. But we are going to develop some special tool and device and agreement among the agencies to achieve the immediate data sharing. Then group D is the group for the flood control. More correctly, the river management, the dam system management. If the flood is predicted, we need to manage the dam to reduce the water height, because we are going to have the heavy rain. Then, but at the same time, that's the kind of dam managed by Ministry of Construction. But we have different dam managed by the Ministry of Agriculture. For them, water is a kind of goal. It's quite important for them, for their life, because they are, their job is related to agriculture. So that's quite difficult to manage such kind of dam. Because the Minister of Construction easily say, okay, reduce the height. But the Minister of Agriculture refused, no. What happens if the water rainfall is less than expected? After the typhoon, they got a serious problem because of the lack of water. So this issue is somehow multi-ministerial issue. The Ministry of Construction and the Ministry of Agriculture are going to discuss how to achieve most reasonable control of dam system. That's a group E. Then group E is a fundamental subgroup to develop the digital twin technique. In Japan, we just started to develop the digital twin world. So, but it takes time to get all information and develop the data structure in the digital space. This kind of digital twin, if we obtain, this kind of digital twin can be used not only for the disaster mitigation, disaster management, but also infrastructure management for daily use. And because of that, the SIP program for the disaster management and Professor Hisada's group, the SIP program for the infrastructure management are collaborating on this issue. So digital twin, the basic digital twin will be constructed by the SIP for not disaster, but the infrastructure management team. They will develop. Then we, disaster management team, will develop a tool on this fundamental digital twin system. Then because the project is huge, many professors and the former central officers are involved in the project. Then the supporting agency is NIEDO, National Institute for Earth Science and Disaster Mitigation. Then Dr. Suzuki is program manager. Then some professors are involved in the managing the project for each subgroup. Then right side is actual researchers to conduct the research. This is the structure of our team. Then the schedule. We have 5 years, but very, very tough program. In the end of 2025, when 3 years has passed, they will evaluate the progress of the project. If they do not satisfy this program, this SIP program will be terminated. So we are not tackling to get a nice result to pass the intermediate evaluation. The one very important issue is this is not academic research only. The government is expecting to apply the output to the public. 5 years later, the new technology should be ready to be used in the public. That's the major requirement from the government. Then after that, with very, very small letters, I'm showing somehow detailed information of each subgroup. But today, unfortunately, I don't have time to touch on the details. So when you have time, please take a look at the detailed information about each subgroup. This one is subgroup A. They are going to use the satellite image and IoT sensors in the buildings and the rivers and drones. Then subgroup B is going to change the people's mind to let them evacuate. And subgroup C is going to develop the new device and framework to share the immediate information among the self-defense agency, police department agency, and the fire department agency. That's the group C. The group D is going to develop a new dam management system for both the Ministry of Construction and the Ministry of Agriculture. Oh, then the group E, the fundamental digital twin space will be developed by the Professor Isada's group. So we are going to develop the software to use the digital twin technique. So far we have two groups. One is, you see like this, that we can estimate the damage of each individual buildings to give the more accurate information to the people. For the people living in that specific building, you should evacuate. The next building is okay, we can stay. Something like this. Then we are going to develop some dynamic risk map right after the disaster happened. The another group is for tsunami. When earthquake happened, it's a matter of time. Immediately they start the calculation to predict the tsunami, tsunami height, inundation area, then who should evacuate. They will do the calculation right after the earthquake. Then by using the supercomputer in Tohoku University, they say that it takes just 3 minutes to predict the tsunami. Then the whole model prediction, the 1 minute to the real-time tsunami simulation and so on. It takes just, they are trying to develop the system so that we can finish the calculation within 4 minutes. It's quite challenging. Then, as I told you, we are going to collaborate with Professor Kisada's infrastructure management program to develop and share the digital twin technique and cyberspace. So, it's almost time, I think. So I would like to show you the concluding remarks. So even disaster mitigation, now it's time to use digital technique. Before that, we didn't believe about the computers, especially right after the disaster. We may lose electricity, the computer will be damaged. We cannot trust, we cannot believe in the computer right after the earthquake. But the time changed. You still use cell phone even after the earthquake. It's getting much, much more trustable. Why don't we use the digital technique even for the disaster management? The situation and the condition and time has been changed. Now it's time to use digital technique. That's what we are going to try to tackle in the near future. Thank you for your kind cooperation. Attention.
Thank you. We will have time for questions at the end. I thought we have a time slot at 13:10 for wrap-up discussions. I would like to invite now Professor Radu from the Technical University of Civil Engineering.
Thank you so much. We are running late somehow, so we will postpone the Q&A session after the coffee break when all the 8 presentations will be completed. I will have a brief presentation about the project we started 1 year and something ago about the seismic risk of bridges in 2 counties that were proposed by the Ministry of Transportation and Infrastructure here in Romania. I mean Vrancea and Buzău due to the very closeness of Vrancea seismic source. Actually, this idea for this project somehow came after we developed several projects with the World Bank, and the prioritization was the main topic, because you have a huge problem, you have a very limited amount of money, you have very limited resources, and how do you prioritize? And we are applying a very rapid procedure. First of all, I will give you some context. We have to apply this simplified PSRI for road bridges in Vrancea and Buzău counties, such as to provide a fast tool to prioritize the seismic retrofitting investment. This is a very brief on probabilistic seismic risk analysis. You can obtain the probability of failure, whatever you are defining as a failure, as a product, a convolution product between hazard and fragility or vulnerability. And here it's an example. With red, we have the hazard, and with blue, we have the fragility, and we may integrate this information such as to come up with some conclusions on the probability of failure. I will go step by step first about the hazard. The hazard usually is defined by seismic hazard curve. And this seismic hazard curve can be simplified as we have for the magnitude of the earthquake. We have a relation where we have two terms, A and B, A being the productivity of the source and B being the slope. It is the same for the seismic hazard curves. We have two parameters, K1 that is giving us the productivity. In other words, how many large ground motions might you have in a given frame of time. And the second parameter is providing the slope. If you have a very mild slope, then the probability of very large ground motions is quite low. If you have a very steep slope, then the probability is quite large. And for the seismic fragility, first we have to define the failure, what failure means. In this example, the failure is defined as the exceedance of the ultimate limit state of the bridge. As usual, for fragility function, we use the most, let's say, advisable approach with log normal distribution function. We take care both of random uncertainties and epistemic uncertainties, and we can define, as it is employed for a very long time in nuclear industry, is that high confidence, low probability of failure capacity. You may define this high confidence, low probability of failure in the median fragility as a 1% non-exceedance value, or you can define it on the 95% fragility curve as a 5% non-exceedance value of the capacity. And in order to avoid that convolution integral that is very tedious and you need all this kind of information, it was a procedure also proposed by nuclear industry, by Kennedy and Short, in a document many years ago, 1994, where the probability of failure can be obtained with several parameters in the hazard curve and in the fragility curve, namely the two parameters of the hazard curve, K1 and KH, and the two parameters of the fragility curve, I mean the median value and the log normal standard deviation of here. As for the seismic hazard, we employed the model that was developed in two projects with our colleagues from National Institute for Earth Physics and in Czech, Bucharest, with 14 seismic sources, but for us, what is most important is what is happening here in Vrancea. And for sure, for bridges in Vrancea, in Buzău counties, the seismic hazard is dominated by Vrancea seismic source. And based on the results from Bix's project and Rory's project, we had already obtained the hazard curves for all the sites that were provided by the Ministry of Transport and Infrastructure in Romania. This is an example of a map, seismic hazard map for Vrancea, And this is a seismic hazard map for Buzău, as I mentioned, obtained in the two previous projects. As for the exposure database, the proposal from the Ministry of Transportation and Infrastructure was with two counties, Vrancea and Buzău. And these are the sites of the bridges that were provided by Ministry of Transport of Romania. And these are the sites of the bridges in Vrancea County. And these are the sites of the bridges in Buzău County. I have to mention that there is no rail bridge, there are only road bridges that are in this exercise. And this is the information for 146 bridges in Vrancea and 81 bridges in Buzău. We have this information from the national company. And for each and every bridge, you have a wealth of information on the bridge. What is very important to us, the location, the structural material, the number of spans, the overall dimension, year of construction, and year of retrofitting, if there was retrofitting for that bridge. As I mentioned, we will use for characterizing the seismic fragility the log normal cumulative distribution function, and there are two parameters: the median capacity and the standard deviation of the logarithm of the capacity. And we took into account two kinds of information. The first information was about the year of construction or the year of retrofitting of the bridge, such as to have an idea about what technical regulations were applicable during the design of the bridge. And also we took into account this database that was developed under the supervision of Professor Kappos, a very large database with many bridges around the world, and it is called an online platform for bridge-specific fragility analysis of as-built and retrofitted bridges. Putting together this information, so the information received from the Ministry of Transport and the information in the database, we decided for some pair of values for the median capacity and the logarithmic standard deviation, based on the different technical regulations imposing the demand for the seismic action. For the capacity for bridges, the bridge engineers, I'm not a bridge engineer, I'm an earthquake engineer, but the bridge engineer used a lot of let's say, regulatory framework that comes from the national regulation or from the Ministry of Transportation. So I refer here just to the demand, and the demand was according to the seismic design codes with different periods in Romania. And you have the design, peak ground acceleration, the median capacity, and the logarithmic standard deviation. And here you have fragility functions for bridges designed, for example, with low code, when you have the yellow line, or the bridges designed with a high code, where you have the green line, something like this. Taking into account these values of the median capacity for the bridges, this is the value for Vrancea at the sites of the bridges. I have to mention that this is not a map for zonation of the seismic fragility. The map just interpolates for the values in discrete points at the sites of the bridges considered in the analysis. And this is a map for Buzău. And putting together all this information and coming back to the relations that was provided by Kennedy and Short in 1994, this is an example of some results we obtained. Of course, for all the bridges, more than 200 bridges, we have this kind of results, but this is just an excerpt from the spreadsheet, and you have the city or the town, the material, reinforced concrete or pre-stressed concrete. This is the example, year of construction, year of retrofitting, if there was retrofitting, the year considered for fragility function, for sure, if the bridge was retrofitting in 2009, we'll consider that 2009 is the appropriate year for the fragility function. And then the values, K1, KH, the median value, the logarithmic standard deviation, probability of failure, but I have to mention this is a nominal probability of failure. And nominal probability of failure is redefined in structural reliability. It's a probability of failure assuming that there is a perfect maintenance for the building and there is no human error. So I don't trust the numbers with the nominal, but anyway you have a matrix. And if you have a matrix, then you can have some idea. And that's why I normalized the probability of failure, and I have a relative probability of failure, taking into account, let's say, the safest bridge, and then how many times the other bridges are more prone to seismic risk as the baseline. And in the last column, I have the high confidence low probability of failure as it is defined in the industry. And here you have a map with the nominal values of annual probability of failure for the bridges in Vrancea County, and the nominal values of annual probability of failure for the bridges in Buzău County. Now, discussing about the limits of the analysis, we have a lot of limits in this analysis, mainly in the fragility function. I think that the reliability in the seismic hazard is much better than in the fragility. And usually this is the problem in engineering, that we have more reliable information, reliable until a very big earthquake, like the Hope earthquake, okay? But anyway, until that, the information is reliable, but with the fragility function, namely the median capacity and the logarithmic standard deviation, there is a lot of work to do. And my colleague Ionuț-Cristian will present you an example very focused on a case study. And for the second phase of the project, we need more in-depth engineering analysis in order to define the values of the median capacity and logarithmic standard deviation with a higher reliability and with higher confidence. And moreover, this analysis took into account, as for the prioritization, in terms of nominal probability of failure, just the seismic risk. But of course, we have to take into account many other parameters. I mean, to correlate it with the technical state of the bridge, to correlate with the traffic importance, the redundancy, because KUSUNOKI-san mentioned that it was a very narrow end of the peninsula, so there are only a few roads, and this might be the case as well, to take into account the redundancy. As I mentioned, the state of maintenance, and putting together all this information to have a list of prioritization of the investments in the bridges. In these two counties, this is only a pilot project. It can be extended nationwide. Muito obrigado a todos.
Thank you. I will introduce now Professor Makoto Hisada from Tohoku University. Professor Hisada is a temporary member of Science, Technology and Innovation Promotion Secretariat at the Cabinet Office at the Government of Japan. Please proceed.
Again, good morning, ladies and gentlemen. This is Sada from Japan. So my presentation is Smart Infrastructure Management System. So this is, first of all, since this is first time to visiting Romania, so this is my introduction. So my research field is concrete engineering, especially maintenance of infrastructures. And this is one of the motivations of my research project. So I experienced the Great East Japan earthquake in the 2011. So you can see the blue is Tokyo, and Sendai is a distance from Tokyo 300 kilometers. And that Tohoku University locates in the Sendai, where Professor Akiyama graduated this university. And you can see that this is my laboratory. So just after the earthquake, and also disaster victim. And I wonder how infrastructure we have to maintain the infrastructures just after the earthquake disaster. So at this workshop, I'd like to learn about the Romanian infrastructure management, the actual situation. And I would like to discuss our future collaboration. And today's presentation contains the background of the and purpose of the presentation situation and issues in infrastructure in Japan, and the SIP third-term program and completing remarks. And now I will move to situations and issues of Japanese infrastructures. So as you can see, the deterioration infrastructures in Japan, we are facing now many risks, such as natural huge disasters and also aging of deterioration. This is one of the Japanese newspaper told us that no civil engineers in local government. So how the Romanian situation, I would like to know. And this is one of the special issues in Japan, such as huge gaps among locality. So we have almost 0.66 million bridges in Japan. And population of Japan is 127 million. Therefore, totally, Japanese people, 192 people have to support one bridges. You can understand? And also there is many gaps, huge gaps among these like this. When in the comparing the regional comparison, Tohoku area is a number of 134. Therefore, the below of the Japanese average. And on the viewpoint of the prefecture comparison, in Tokyo area, such kind of many population, they can support one bridges as a 3.3 3,300だから3,300 people. However, in Shimane Prefecture, where locates far from Tokyo, they have to only 51 people for one bridges. ultimate gap, we can see in Tokyo, 10 million people for one bridges. However, in the local government, have to support the one bridges for by only 5 people. So the range of gap is almost 20,000. So this is one of the main issues in Japanese situation. And I will present about society 5.0. So this is technology and innovation basic plan of Japan. So the society that Japan is aiming for, society 5.0, which are going to realize a sustainable and resilient society that ensures the safety and security of its citizens. And also, the society 5.0 is a society in which the diverse well-being of each individual can be realized. So, what is 5.0? We determine the society 1.0 is hunting and gathering. And society 2.0 means agriculture society. And also society 3.0 means the industrial society. And society 4.0, which maybe we are now in this society, means information. And after that, we are going to realize that new society as society 5.0. So this is one of the images of the society 5.0. So you can see the many future situation. And also we can see even in the future society, we automatically drawing the road like this one, and also some kind of infrastructures in the future society. Therefore, we have to support even not only the present society, but also future society by the some kind of infrastructures. And I present the SIP3 program of infrastructures. So as Professor KUSUNOKI present you the outline of the SIP term 1 and term 2 and term 3. And the Cabinet Office prepared mainly 3 big project. One is a cross-ministerial strategic innovation promotion program as a SIP. And second one is a program for bringing the gap between and the ideal society and generating economic and social value. We call the bridge. And third one also moonshot project. And mentioning the infrastructures, we have this history. During the phase 1, we did infrastructure maintenance project. And as phase 2, we didn't have this project. And from 2023, we restart the establishment of smart infrastructure management system. And in the SIP phase 3, we have some special concept. 5 indicates for social implementations. From the SIP 1 and from SIP 2, we learned it was difficult to move forward by only focusing on technology. Therefore, we considered about the 5 viewpoints for social implementation. Not only technology, but also some kind of systems and also business and social acceptabilities and human resources. And this is the 14 project which promotes in the SIP third terms. So you can see the infrastructure management system here, and also smart disaster prevention network, which promotes Professor KUSUNOKI. And our program establishment start smart infrastructure management system contains 5 projects and 10 sub-projects, and more than 700 researchers in 130 institutions. And now we are in the second year of the 5-year term. And this is a vision for the future. We prepare the 3 layers of smart. One is future construction technology. And second one is future infrastructure, which means smart infrastructures. And third one is smart city, which contains both of the future technology and future infrastructures. And this one is our project in details, but this is very busy slide, so please check after the presentation. I can give my handout. So this the other project A, innovation in construction production processes, which manages from design to construction. And second one is building an advanced infrastructure maintenance cycles from the building, from the construction after the during the maintenance terms. And third one is the strategic utilization of human resources for infrastructure management in local government. And fourth, project D, development and application of infrastructure data platform for cyber and physical spaces. And fifth one is creating attractive national land, cities, and regional through smart infrastructures. And these 5 projects can construct the 3 layers, and this is all over our project outlines. And also, I will give the members of this project. As a program director, I am a program director of this project, and Professor Akiyama manages as a sub-program director here. And this is also the project management team. Each project from A, B to E. And this one is principal investigators. As a project A is Professor Kenji Nagatani, and as B maintenance, Professor Tetsuya Ishida, and project C is Professor Shinichi Miyazato and Professor Kazuhide Sawada. And project D is Riki Honda and Hiroya Maeda and Takahiro Kumura. And as project E is Professor Akinobu Murakami and Professor Sadaharu Kusuba and Professor Kiyoyuki Kaito. And as a concluding remarks, to summarize, infrastructures in Japan is facing a lot of difficulties to operate due to aging infrastructures and society, as well as more severe disasters due to climate changes. And to break through these situations, we conduct a 33 program as a smart infrastructure management system starting in 2023. And the program aims realize society 5.0 by creating future construction technologies and infrastructure and future cities. And also, we are eager to establish collaboration with participants of this workshop, such as collaboration research or business development, implementing technology in Romania and Europe. And also, it is our great pleasure for solving similar issues in Romania by referring our research fruits. Thank you for your kind attention.
Thank you very much. I will introduce now Professor Ionuț-Cristian from the Technical University of Civil Engineering of Bucharest with the presentation Seismic Fragility of Bridges Case Studies.
Hello everybody, my name is Ionuț-Cristian. I am an associate professor at the Department of Strength of Materials, Bridges and Tunnels in our university. And I will make a short presentation of a practical study we made on a bridge in Romania. A practical study we made on a bridge in Romania in order to show the benefits of considering the analysis in terms of fragility curves for the safety of bridges. So the contents of my presentation is here. It will be a short introduction about the methods usually that we take in bridges for for primary analysis on seismic study. Then a short description of the bridge, modeling of the structure, some results following the performed analysis, and some conclusions. So the term of fragility curve is not so quite well known in Romania because we didn't use this concept till now in the study of bridges for the seismic action. So mainly there are several types of analysis commonly used for bridges design, seismic bridges design, and here are these methods of analysis. There are two major methods, force-based methods, mainly dealing with linear analysis, and in this kind of methods there are several assumptions. So we have, because of considering the linearity of the phenomenon, there are quite a lot of parameters. They are not evolving, so you can see them there. And for this reason, we do not consider that the general stiffness of the structure is affected. A lot of our bridges designed in early years in Romania till 70s, 80s, they were calculated using the equivalent static lateral force method, so a static analysis. And it was interesting for us to see how they deal with other levels of the seismic hazard, because in this kind of primary analysis, a lot of factors they were taken into account. So as you know already, the input for these simplified methods are some lateral forces acting on the structure. Of course, in bridges, the case is a lot of mass is distributed at the level of the superstructure, and the results were in terms of structural displacement and element internal forces. A much more evolved method of analysis is so-called response spectrum analysis, which is it's in the category of dynamic analysis, and with the new issues of the Romanian code P100, even for bridges, we could take from there as input the seismic spectra. Of course, we have also the Euro codes, and there are a lot of provisions there. But in my opinion, the spectra in Euro codes are not so good for describing the seismic action in Romania. But this is another issue, and I will not address it here. So, considering the response spectra, the results are the same as for the simplified method. For a specified level of the seismic hazard, we will obtain the displacement, the structural displacement, and the level of the stresses on the cross section of the structural elements. For us, a big interest is the displacement at the superstructure level, because of the need to design the expansion joints and the anti-seismic devices. Then another category is the time history analysis, a linear time history analysis, having as input the recorded artificially generated accelerograms, which should be made compatible with the response spectra. Of course, here is a problem, because in order to perform satisfying from the result points of view analysis, we need to have recorded accelegrams, but we don't have it. So we have some recorded accelegrams at the disposal, but mainly we use artificially generated accelegrams. And the second category, major category of methods, are so-called displacement-based methods. They are dealing mostly with nonlinear analysis, and this is the case where we consider the evolution of the and the degradation of the structural components by the meaning of the parameters characterizing the material and also the stiffness of the structure. Pushover analysis is one of these methods, and the method practically starts with considering some lateral forces and increasing it until some weak points appears on the structure. And the results, mainly it's a representation between the base shear and the structural displacement. A much more evolved method proposed in the literature existing at this time is the so-called capacity spectrum method. A version of this method was first introduced by Freeman around the 70s, and this is a combination with the pushover analysis. The idea is to plot the spectra for a specific site in a special format, acceleration displacement ADRS format. Of course, also the pushover curve should be translated in the same format, and by using both all curves at the intersection between the pushover curve by the intersection of pushover curves and the other curves defining the spectra, we can find so-called the performance point of the bridge in terms of seismic resistance. Of course, there are also nonlinear time history analysis. The difference between the linear one and the nonlinear one is, as you know, the input is almost the same, but beside the inputs in terms of accelerations, we use also some other inputs describing the nonlinear behavior of the materials and characteristic of the cross-section of the structural elements. Of course, here the response is much more evolved, so we can find out the evolution in time of some parameters, needed parameters, or displacements or internal forces, but also the behavior of the structure in the weak points that can appear during the earthquake action. This analysis can be used also to estimate the performance level of a structure in terms of displacements or forces. Today I will present a study, as I told you before, but this study deals with the determination of the fragility curves for a bridge in Romania. The analysis is based on this concept in incremental dynamic analysis. In fact, this analysis is based on the nonlinear time history analysis. Uses as input some artificially generated accelerograms, which were scaled to comply with different levels of the seismic hazard. Then, by interpreting the IDA curves by the meaning of some limit criteria we imposed for this particular bridge, we can estimate the behavior of the bridge not only for the base earthquake, therefore the bridge was designed several years ago, but also we can have a prediction of how the bridge will behave for other levels of the seismic hazard. The bridge is placed on in Bistrița County, Romania, and you can see here the characteristics of the site. So peak ground acceleration 0.1 G and 0.7 seconds the corner period. This is the bridge layout. It has 7 spans, 2 massive abutments and 5 massive piers. And the foundation system is consists in shallow foundations. So the spans are not so large. You can see it's they are in a medium range of spans of around 40 meters. This is a current cross section of the bridge. You can see the pier geometry, the elevation of the pier, its foundation, and the superstructure, which is consisting in 5 precast concrete girder having at the top part concrete slab. It's a road bridge. The model of the final element of the bridge is not so complicated because we were not interested on what is happening on the superstructure level. So all characteristics of the superstructure were grouped into a single line, and you can see also a detail how we have modeled the elastomeric bearings and also the isolators, because the bridge has 2 different kinds of bearings. On the buttons, they are classic bearings, European bearings with very low height, and on the piers, there are some kind of bearings similar to the high damping isolators, high damping rubber bearings. So these are the curves describing the behavior of the used bearings and isolators. And here are the characteristics introduced for the plastic hinges considered at the base of the piers. There in the second graph, D, C, D, E, they are not the performance levels usually inputted in some kind of software. Are only the A, B, C, D, E are the points we find in the backbone curve. So the points characterizing the performance levels should be between BC and CD respectively. The plastic hinge was a deformation control one, where the plastic hinges were deformation control one, based on the interaction between the axial force and bending moment, because the cross section of the pier, it's, as you see, massive, so it is developing also an important component of the bending moment in the longitudinal direction. So as input, we use 10 artificially generated accelerograms, which are compatibilized with the response spectrum on the site. You can see also the target response spectrum, the mean response spectrum, and also the corresponding displacement spectra. Each accelerogram were scaled in order to comply with several levels of the seismic hazard. You can see on the right, I will make a mention here. We have considered as reference period of occurrence 100 years because the bridge was designed considering this level of the seismic hazard. So we want to see what is happening for other levels starting from this one. So you can see the scaling coefficients. We use here the S exponent K 0.3. There are some other provision literature. For example, Jonco and Marzolani, they suggest for K to have even a lower value, 0.28. But we want to be in this range, 0.4, which was indicated by much many documents. This is the moment curvature plot for the cross section of one of the piers. By the end of this, we have established the yield displacement, and when I say yield displacement, I refer to the reinforcement, and also the ultimate displacement. And as you can see, the estimated values there on the right for the rotations and for the displacements. And by performing a lot of nonlinear time history analysis, we can establish the so-called IDA curves, which are the representations of the surge parameters, in this case displacements at the top of the piers, and the rotations in the plastic hinges at the base of the pier. We have limited, and we search the displacements at the top of the piers because we're interested to see if the expansion joints in the first stage they can accommodate with the displacement, with the displacement produced by the earthquake at different levels of the seismic hazard. So the representation of the displacements and the rotations versus the level of the seismic hazard. And you can see the limits there for the displacements and rotations for yielding of the reinforcement and ultimate displacement. And further on, we use these values of the displacements and rotations by the end of the end of a probabilistic analysis, and take into account that the suggestions in the literature is that all these values for the displacements and rotation respect a log normal distribution. We check this, and it is almost quite this. So starting from this assumption, we trace the fragility curves for this bridge. In the first stage, we determine the probability density functions and for each level of the seismic hazard, and then the cumulative distribution functions. And interpreting the limit values we imposed in terms of displacements and rotation, excuse me, we could establish the probability of non-exceedance for each level of the seismic hazard. Here are represented only 4 levels of the seismic hazard, as you see. The base earthquake with the period of occurrence of 100 years, and then 475 years, 970 to 1,400 years. This is in terms, these graphs are for displacements, and the corresponding graphs for rotation in the plastic hinges at the base of the piers. I choose also to show you a plot of rotation, in a plastic hinge for the tallest pier before. This is for return this corresponds to an earthquake with a return period of 475 years. As you see, the limit displacement we imposed, the limit rotation we imposed, 2 promille was, even for this earthquake, exceeded. The main conclusions, you can see it there. In terms of displacement, the bridge behaves very good, or let's say quite well for different levels of the seismic hazards. So until 970 years, in our opinion, this bridge has a satisfactory reserve. But in terms of rotation, the problem appears even for not so high level of the seismic hazard. And this can be better seen from the fragility curves. As you see, it is a reserve only of 23% for the earthquake, with a return period of 475 years, and 13% for an earthquake with a return period of 970 years. So as a conclusion, as we expected, because as I said, the bridge was designed taking into account the old norms in Romania. As we expected, the bridge will suffer some damages, starting with an earthquake with a return period of 475 years. So we should enlarge this kind of analysis for other bridges in Romania, main bridges or also secondary bridges existing on the Romanian infrastructure network. Thank you very much for your attention.
Thank you very much, Professor. We will conclude this session. I invite you to the coffee break here in the main lobby at the same floor. You can find there coffee, and I've heard there are also Japanese sweets, so please, you are invited.
Viitorul e al tău, noi punem temelia.